redundancy elimination or common sub-expression elimination. So why partial redundancy elimination is important? Because it allows you to do optimizations on such programs also. In fact, PRE is a very strong optimization. Partial redundancy. It encompasses several other optimizations and we'll see that. Okay. So another thing I want to show is, I have an example which we will try to solve. So this is in SSA form. Okay. But for PRE or partial redundancy elimination perspective, you can ignore version number. You can see A plus B is computed here, A plus B is computed here, A plus B is computed here, A plus B is computed here. Okay. Can you see that all these A plus B, some of them are redundant, some of them are partially redundant? Just intuitively, can you tell me which ones are redundant, which ones are not redundant? 6 is redundant, because no matter how you come to 6, you will execute 3 before it. 3 already computes A plus B, so that is redundant. What about 5? It is not redundant. Okay. So even though 3 and 5 are computing same version, same variables, but you have to do both. What about the later on 14? Is it redundant or is it not? Is it partially redundant? Forget about 5 for some time, 5 and versions. So if I ignore these 5s, A6, A plus B is computed here, you go along the loop, again A is computed here. Okay, so you hit same A plus B. 5s are just copying variables, they are not real assignments, so you can ignore them. Similarly, along 5 path it is computed, but along this path it is not computed. Okay, so certain path it is computed, certain path it is not computed, which means it is partially available in 14. Now think about it, if you can, like we said, if I just move one computation here, a copy here, computation here, I will be able to remove this computation. But then the advantage will be any looping path. Currently you are computing it in every iteration. If I can move it out of the loop, you have to compute it only once, and every iteration of loop can use it. Again, I am assuming internally it does not change. Okay, have you heard about this kind of optimization where you move code that does not depend on loop variables? You can move it outside the loop. Loop invariant code motion. So I have a code like for I equal to 0, I less than 10, I plus plus, x equal to y plus z. Okay, and both y and z are not affected by the loop. So there is no point in computing it 10 times. I can simply move it out of the loop, compute it only once and use it, and then I can say maybe print x here. So I only have to print x 10 times, compute it only once. Okay, same thing is happening here. So this partial redundancy elimination, if you now look at it this way, so generally when you have while loop, So I less than 10 is false. And it is true. This is my program. Okay. So what can I do to optimize this program? Is it readable? Let me just delete this part also. And so how do you optimize this program? This is I less than 10. I don't know if it is readable or not. Up, okay. What do you mean by up? Where should I put it? Should I put it here? So you are saying if I remove it from here to here, jump here. No, that's what I am asking. Can you come up with a situation when it is not allowed? Yes. Okay. So this is not entry of the loop. This is the body of the loop. Okay. So let me. Okay. So I mean, in this case, maybe it's because you have very simple program. You are moving it here. So then while loop की भी क्या जरूरत है like that. So maybe there are other things also. Let's say X is being used here. Okay, so now you cannot move it here. So you move it before the while loop. Where? Here? Then here. Okay. I insert a block or put it here itself? Okay. So let me just, okay, in fact, so let me change this to y is equal to input from the user. Okay, and then you are saying x equal to y plus z here, and this I will remove. Okay. Do you see any problem with this change, or everything will be good? Yes. No, that part is taken care of. X, Y, Z are all defined. That you have to take care of, but assume that is taken care of. If the loop doesn't execute, means initially I is greater than 10, then what happens? In original program, you are not computing y plus z. But in the modified program, you are computing y plus z. So there are certain paths where your program is becoming complex or more time taking. Okay. Now not just that, the expression could be such that it might generate an exception. Okay. That is possible. I mean, it might be divide by zero kind of thing. In original program, because the program did not execute the expression, no exception was generated on certain path. But now because you have introduced it, it might generate an exception. Okay. So whenever you are introducing an expression, you have to ask these questions. Am I introducing extra computation? Am I introducing some chance that the program will generate an exception? So anytime when you are introducing a computation in your program, the rule of thumb is, if there is a path where computation was not there, you should never introduce it. Okay, because it can create, you run this program, maybe y plus z overflows, an exception is generated, and user sees that exception, he sees I is greater than 10, why is y plus z been executed? I did not want it to execute. Are you able to understand, follow? Yes. So let's say this is an expression, maybe y is very big number. And z is also a very big number, and somewhere you are capturing that addition does not overflow. Okay, the moment you do y plus z, if there is an overflow, some exception is generated. All these kind of things are possible. Or okay, or maybe let me make it simpler. Z is 0 and x, the expression is y divided by z. Okay. User says that, okay, I will always give I which is greater than 10, which means this path is never executed, which means my program will run through. But when you execute your program, because of optimization, you do 10,000 by 0, you get a divide by 0 error. Now user is confused because user sees this program. User is seeing program where y divided by z should not have happened because I is greater than 10. So he says I gave I greater than 10. Where is this y exception divided by 0 coming in? I don't see any place where I am dividing by 0. Compiler has happily moved code around and created an extra expression which is kind of invisible to user. Will you be happy in such cases? You write a program, you want to show it to your instructor, and the program gives an exception divide by 0. And you try to debug it, you are not able to find that division anywhere in your program. Okay, so that is why if you are introducing, on the other hand, suppose you have already written it here or here, then at least you know that, oh, it's my mistake. Line 1 or 2 here and there might be some architectural issue, but at least you are expecting this division by 0 to happen. So the rule of thumb of optimization says, never introduce a computation on a path where it is not originally there. Location can change in the path, okay, but it should not come suddenly out of nowhere. Okay. So are there any other, then how do you optimize such a program? So basically you avoid computation in what is called such paths where computation is not already there. So how do we know computation is there? So given a point, there are two ways you can fix it. One is from entry to this point, computation should exist on all path. This is what you call available expression. We have already done this. There is a mirror image of this also. Maybe computation is not available on all path. On the other hand, from P to exit, computation exists on all paths. So no matter how you run the program, when you go from P to exit, there is a computation. In this case also, it is good, it is okay to move computation to this point. In this case also it is okay to move computation to this point. So as long as one of this is true, either expression is available, what you have done already, on all path it is available, you can move the computation to the availability point where it is available. Because no matter if you execute original program, computation is going to happen. In your new program also computation is going to happen. Okay. The other case is, let's say available expression is not available, but from P to exit, on every path it is going to execute, it's going to be computed. Then also you can move it from here to here. You can introduce a new computation here of C. This is called a mirror of available expression. It is called anticipable expression. You are anticipating that it is going to happen. Okay. The analysis, this is the fourth classic analysis. It's just a mirror image of available expression. It's the backward analysis corresponding to available expression. You have to, from P to exit, on every path you have to check for a computation. So if it is available or anticipable at a point, then it is safe to introduce a new computation of that expression. Okay. In available expression, we always do that. Okay. In anticipable expression, we have not yet seen, so we'll kind of wait for that. But in partially available, this is a challenge. If you are introducing, like we did for our simple programs, you have to make sure that at least one computation exists on such a path. Okay. So SSA PRE is a very interesting analysis. As I said, it's one of the complex analysis which does all that. And that's why it is not a single analysis, it's a collection of multiple analysis, but then at the end you get lot of optimization, because you get code movement, you get loop invariant code motion, you get partial redundancy elimination, partial availability handled, and there are other strength reduction and few more. Okay. So let me. So PRE can be done without SSA also, like any other optimization. It has been, in fact, for a time it was very, very popular analysis. It became kind of the holy grail that everybody wanted to do PRE using data flow analysis and improve it. So lot of variations are proposed in literature. It uses availability, as I said, it uses anticipability, it uses partial availability, it uses partial anticipability. So all kind of things it uses to decide whether I can convert a partial redundancy into a full redundancy, or partial availability into full availability, and then remove the redundancy. Okay. So it identifies partially redundant computation, make them fully redundant by inserting new computations. And because it is inserting new computation, it requires availability or anticipability. And finally, now the computation is redundant, fully redundant, so you can do CSE. Okay. So like any other data flow analysis, it's an iteration based, you do multiple iteration till you reach fixed point, but it is a collection of multiple data flow analysis. So each of them has to terminate or reach a fixed point. Then it works on control flow graph, and it also requires you to compute global and local versions of data flow analysis, like you must have done for available expression. Okay. So as you can see that it's a quite involved exercise, and it is not so efficient. Okay, you have to iterate and reach fixed point for multiple such data flow analysis. So that is why SSA PRE is much more lucrative proposition, because once again SSA PRE avoids going over all the control flow edges. It can flow information along SSA edges. It does not need to maintain separate global and separate local information. But there is a challenge. Whatever we have seen SSA, it was only for variables. Now we need SSA form for expression. Okay. Given SSA form for variables, you have to identify redundant expressions. Now what may happen? Why it is a challenge? Because it may happen that on one path you are having A1 plus B2, on another path you are having A5 plus B3. Okay, and there is no computation of AB after this. Then you have to introduce a phi function for A, phi function for B, and there exists some computation of A plus B here. Okay, now how do you know whether this A plus B is redundant or not? It is redundant because A1 plus B2 is the last computation of A plus B, A5 plus B3 is the last computation of A plus B, phi is just conceptual entity which is only moving A, B around, it's not actually changing A1 or A5. So this is also redundant. But how do you figure that out? Okay, or in some cases, there might be another assignment to A here. Okay, how do you distinguish between previous case and this case, that now A has changed? Earlier A has not changed. Okay, version numbers will keep changing. So here is an example, concrete example. Is A3 plus B1 partially redundant or not? So if you take strict view that A3 is a different variable than A1, then A1 plus B1 and A3 plus B1 are totally different expressions. Okay, if you are very strict. Okay, for SSA when we talked about it, we were very strict. We were thinking A1 is a different variable, A3 is a different variable once we number them. But when we come to PRE with SSA, now you have to go back to the saying, oh, they are different versions of same variable. So I should treat them same for SSA PRE. I treat them different for SSA, but for SSA PRE they should be treated as same. Okay. In fact, you also have to worry about that this version number is coming, change is coming only from phi, not from actual assignment. So again, it's kind of going against the philosophy of SSA. We did not want to distinguish between regular assignment and phi assignments, but now you have to worry about them. Phi is just a conceptual entity, it vanishes when you are talking about similarity of expressions. But it is useful when you are talking about variables themselves. Okay, is this clear? Is this point? Okay. Once again, for SSA, it is important to have this distinction between A3 and A1. Because A3 says sometimes I am A1, sometimes I am A2. Okay. On the other hand, for SSA PRE, you have to hide the version number to check A plus B and A plus B are same. You cannot say A1 plus B1 is not same as A3 plus B1. If you do that, then there is no redundancy. Okay, redundancy comes because these two are computing the same value, and phi assignment is just a placeholder. It does not actually change A1 or A3. So then the key idea within SSA PRE was to treat expressions also as a special class of variables. Okay, forget about the name, it's just given by the paper. So this is a new type of variable called RCVs, and then you use some internal variables to represent them. So we'll use H because it's readable. So A, B, C, D are our program variables. H's will be our PRE expressions. Okay, so we will use H to represent some expression E. Now when you say, okay, there is another interesting thing about PRE. In case of variables, it's very easy to say which is definition and which is use. Okay, if variable appears on the left hand side, it is a definition. If the variable occurs on the right hand side, it is a use. Now in case of expression, I have an A star B computation here, and later I have another A star B computation. Okay, I am marking them as H, not worrying about SSA form yet. Okay, I am saying I will mark them as a new type of variable called H. But look at this. This is the first computation of A star B. It is like H is getting defined. This is second computation of A star B. This is where H will get used. Is the distinction clear? This is the first computation which is making this computation redundant. So even though both of them are looking like exactly the same, something equal A star B, this is not redundant, this is redundant. It's like newly you are creating the expression, here you are reusing it. So this is more like definition of H and this is use of H. We might have to, we'll see how we do it, but at this point the challenge is, how can I just by looking at A star B decide is it the first computation or is it the redundant computation? Okay, first computation is like creation, second computation is like use, reuse. So this is a definition, this is a use. So yes, I have to create some kind of SSA edge between them where I mark this as def and mark this as use. But H is the temporary. Okay. No, but that's what I'm saying. Looking at these two statements or looking at just this statement, I don't know anything below, I don't know anything above. Can I say whether A star B is computed first time or second time? No, we can't. So, however, can you tell me whether Z is defined here or used here? So, very clearly with variables, just by looking at the statement, you know is it a definition or is it a use? Just by looking at this statement, I know Z is defined, A and B are used. I don't have to see above, I don't have to see below. Okay, but just looking at this A star B, can you tell me whether it is the first use or second use or fifth use? You can't. Okay, in other words, for redundancy elimination, first computation is definition, any other computation is use in the same line, in the same path. Okay, but just by looking at one point, you cannot tell me whether it is definition or use. So that becomes a challenge. So computation of an expression in itself can represent a def or a use. You have to look at context to figure out whether it is def or whether it is use or the whole path. So if it is a definition, if it is first time E is used, then you are going to use it as a definition or store. If it is second computation, then it is a use, you have to load from H. So this is like temporary, H is our temporary. Okay. Now assuming you resolve these issues, then things become easier. Now you do a PRE on SSA form of H to remove redundancies. Okay. But I mean this is challenge. We'll see. It's a bit, and again I am warning you not to intimidate you or make you run away from the class. But this is a very complex analysis. You should appreciate the beauty of it. Even if you don't understand it, you should understand why it has been broken into small concepts, individual concepts based on what you have done in data flow analysis, or at least we have referred to. Okay, and together they make such a complex analysis much easier to implement. Understanding will take some time, but implementation is very easy. Okay, once you have SSA based SSA based intermediate representation. Okay, it involves lot of algorithms, so it's a thick book. It will take time to read it, but it's a very interesting book. Okay, so final program will be in SSA form. Okay, even before we start, the challenges like critical edges, I referred to critical edge when we were talking about coming out of SSA form. We were having an edge which was kind of time traversing. Okay, so such kind of edges are called critical edges. There's a definition, I don't know if it is here or not. So in a control flow graph, what is a critical edge? It's a node so this will be critical edge, this one. It's an edge from a node with more than one successor. Oh, sorry, not this one. I made a mistake. This one. Or maybe I can make it all right. This is my critical edge. Edge from a node with more than one successor to a node with more than one predecessor. Okay, so this has two successors, 1 and 2, and this has two predecessors, 1 and 2. Okay, so I can even, I need all these three edges. Why such an edge is a problem? Intuitively, so edge from a node with more than one successor to a node with more than one predecessor. So this kind of edge is a problem. Especially when you are having data flowing in both directions, forward and backward, because data comes from here. In actual execution, these two are totally isolated. Any information coming here cannot go here. Okay, so maybe they are from entry. There is some path to this guy, some path to this other guy. These are two isolated regions. They are not interfering with each other. But when you do data flow backward and forward, two bidirectional data flow or two single directional data flow forward and backward, information from here comes here and then moves on this direction, in this direction. Because you remember data flow analysis, you don't keep track of paths, you only keep track of predecessor and successors. Okay, so you take all the information from its predecessors, all information come here. If you move anything to predecessor, information coming from here will also go here. Similarly, information coming from here will go here. So it makes your analysis imprecise. That is one point. Secondly, it causes those issues where if you are inserting a computation on one path, it might create effects on other path, undesired effects. Okay, how do you solve this problem? As I said, this is a standard issue, so solution is also standard. You introduce a new node in between. Okay, now there is no critical edge. So you either have a single predecessor or have a single successor. So this person has a single predecessor and this person also single successor. Okay, this one only single successor, this one has two predecessor, but there is no cross connections. So this solves your issue. Secondly, you have to go through, so this is one part, you split critical edges, then you have to have a pass over the program to identify identical expressions. They may or may not be common, which means there might be recomputation in between, but you have to structurally identical computations. All occurrences of A star be in the program. Okay, ignoring the version numbers of the operand. This also you have to do. Again, this need not be a separate pass, it can be done along with while you are converting to SSA form. Okay, so A3 plus B1 and A1 plus B1 are called identical. I am not calling them available, I am calling them structurally identical. Now you can see that why I say this is a complex algorithm. It has 6 steps. There is a phi insertion algorithm. Note that this phi is drawn different from other phi. Okay, we will see that when I draw both of them. So this phi is for our redundancy class variables, H's only, expressions. Earlier phi is for variables. Again, you have to do renaming. So you have to treat newly created class of variable as any other variable. You have to have phi for them, you have to have renaming for them. Then you have to compute down safety. So down safety this is something what we discussed earlier. If I am introducing a new computation, is it going to be safe or not? Okay, it should not create extra computation on a path where something was not there. You do will be available computation where all this computation will be available if I insert it. Then you do finalization. Basically these two things allow you to find safe positions to insert, but then finalization actually decides where to insert, and once you have decided all this, you have to remove redundant computations. So that is what code motion is, actual movement of code. So movement is like deleting at one place and introducing at another place. So everything, so one simple thing like taking this expression from here and putting it somewhere else has been split into multiple analysis. Each of them does very small simple tasks. Together they do SSAPRE. Okay. So here is an example. If you want, you can please draw it. I may not be having it on all the cases, in all the slides. And as you are drawing it, can you tell me what are redundant expressions, or what are the, so we are talking about A plus B. Okay, there are two computations, one is here, one is here. Which of them are partially redundant, which of them are source, which of them are destinations or def and use. So you just ask these questions before we move ahead. So, has everyone completed drawing? So, can you tell me if this computation is partially redundant? Is it fully redundant? First thing. So, there are at least two incoming paths. There are many because of loop, but these two paths, is it available on all paths? A plus B, ignore version number and ignore phi's for now. It is available, A plus B, you come here and you come here, it is available. Phi's are transparent, okay. What about this path? Full available. So along this edge it is not available, right? You are reassigning A. No, A2 is by phi. Phi we ignore. Phi is like a transparent thing. Okay. So on this path there is no non-phi assignment to A. Okay. So that's why, okay, for simplicity ignore all phi's, delete them from your mental model. Only real assignments remain. So only real things remain. A plus B here, A assigned here, A plus B here. So it is available on one path, at least one path. It is not available on at least one path. Okay, there can be more things, but these two things tell us it is partially available. This one. What about this one? So if we come like this, A1 here, here, this path 1, 2. On this path, A plus B is not computed. I start here, come here, come here. A plus B is not computed yet, so it is not available. But if we take this path, here, 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 come here, then A plus B is computed. So this is a very interesting case. Both occurrences are partially available. Do you get it? Both occurrences, there are paths along which they are available. There are paths along which they are not available. It's quite interesting case. So which one is def, which one is use? Any guesses? And again, make wrong guesses, because when you see the right solution, you will realize, oh, this is what the mistake I made. It will help you recall it later when you see similar example. There is a cyclic dependency, yes, in some sense. Okay, so one thing could be, def could be separate for first and second, but where is that def? So which one is def? So this is interesting because actual def will come from newly inserted definition. So we will insert it somewhere, that will play as a def role. Both of them will become kind of use roles. We'll see as we progress. Okay. So what are the 6 steps? Phi insertion for redundancy class. Look at this phi is different from that phi. Okay, it's very minor, subtle difference, but this is a small phi, that is a capital phi. Okay. So phi and straight line, this is straight line, that is slightly slanted. So phi for an expression E is required when two potentially different values of the expression merge. Okay, it's just like variables. Two different values of a variable merge, you introduce phi for variable. Two different values for an expression merge, you introduce a phi for expression. Like variables, it also happens at iterated dominance frontier. You also have to introduce it at each block having a phi for some argument of capital E. Okay, so let's say E is A star B. Wherever there is a phi for A or a phi for B or both, you have to introduce a capital phi for E. So this phi and this phi are different. Now hopefully you can see that. So phi for an expression will be inserted at two different kind of locations. First location is iterated dominance frontier, just like a variable, because two different values are coming in and you have to kind of pick one of them when executing. It's very similar to variable. Okay. Other thing is, whenever there is a phi for a component of E, you also introduce a phi for E. Intuition for this, anything, why we do this, why should we do this? It comes from this first reason itself. If there is a phi for A, what does that tell you? It means two potentially different values for A are coming in, which means if expression E is using A, two different values of E are possible. Okay. It's like capital phi or small phi. Okay, phi of A will result into phi of E, capital phi of E. So I have to create a merge point for E wherever two different values for E are coming in. Okay. Now it can happen that really two different computations are sending value, which is captured by iterated dominance frontier. On the other hand, it is possible that argument itself is changing, having two different values. So if argument is changing, value of E will change, which means I have to capture it using another phi there. This may not be iterated dominance frontier of E. It might be iterated dominance frontier of small a or small b. Okay? Not clear? No. It's a concept. What I'm saying, okay, at these points it is phi of this phi. But what about other things? I have a plus b on one path, a plus b on another path. A and b are not changing on each path. So there will be no phi for small a, no phi for capital A. or small b. Again, we will come back. Okay. What I am saying, you are capturing all potential points where two different values of E merge. It can happen because you have two different computation of E. It can happen because you have two different computation of A, which is part of E, or B, which is part of E. Reaching expression, not live. We did reaching definition, we are doing reaching definition here for expressions. Okay, but the challenge, as I said, is finding out what is the definition. All this has to be taken care of. So this is potential change in expression value being captured. So exactly, so change in values we are changing. Live means where it is used. We are looking at where is it computed. Okay. So then, again, I have not shown you dominance frontier, but clearly I need a phi here because of phi for A. Okay. Here you can see on one path A star B is little different value, on another path A star B, A plus B will have a different value. So therefore you need a phi here. These are only two merge points. So it's a very trivial kind of example, but this phi and this phi have been introduced for A plus B. Already SSA form introduced this phi for only A. Okay. Now you have to do renaming, which is also similar to SSA variable renaming. You have to maintain a stack of every expression, and then there are three kinds of occurrences. One is real occurrence. In program, as a programmer, you have written A plus B. Okay. The second occurrence is because phi for A plus B has been inserted in the previous step, and result of this you are looking at. And third occurrence is because this phi will have operands which are also expressions, same expression. All three represent the same expression. Okay. So basically your E will be like this, right? E1, it will be H really, equal to phi of some E2 comma E3. And somewhere you also have in your program, let's say W equal to some expression E. So this is one kind of occurrence, and each of E is A star B, or some version of A star B. So this is what programmer has explicitly typed in the program, coded in the program. This phi you have introduced as part of your SSA formation. Okay. Now this phi will have some arguments which are expression, and the result will also be the same expression. So there are three kinds of occurrence, 1, 2 and 3. So after renaming, if somehow you have figured out two instances are same, they will have same H value, same version for H, just like in case of variables. Two different usage, if they correspond to same definition, they get same version number. Okay. So again, at this point it is very similar to variable SSA. Now suppose you find H1 and H2 in your program. So somewhere your A star B converted into H1, somewhere it got converted into H2. Why would that happen? So potentially it is representing two different computations of A star B, or A plus, what did I say? A plus B, right? If I am getting two different versions, which means they are corresponding to two different definitions. I am just referring to SSA for variable kind of thing. Okay. So H1 is a different value for A star B, H2 is a different value for A star B. Why would that happen? It will happen because either A changed or B changed or something else happened. Yes. So it happened because you did some assignment to an operand. Between H1 and H2, there has been assignment to one of the operand, which cause the change in value, right? Or as he said, it is because two different values are coming along two different paths, they got merged, and therefore a new definition has been inserted, phi definition. Okay. If between H1 and H2 neither A changed nor B changed, then H will also not change. Suppose there is a straight line path, no branching, A did not change, B did not change, then why should E change? So then H1 and H2 will remain same, it's H1 and H1. Okay, if they are changed, that means you did something in between, you tried to change either A or B. That is one case. Other cases, maybe there is an H3 coming along some other path, and here you got them merged together. So H2 became phi of H1 and H3. Okay, so this thing can only happen at these two places. So basically, if I have H1 here, H2 here, in between I will see an assignment to A or B, or a merge point such that phi function for E has been inserted. Okay, so rename algorithm, it's slightly different, but again you don't have to run it separately, you can do along with variable renaming. So after you have inserted trivial phi for variables, you can also insert phi for expressions and do renaming together. Okay, whenever you find an expression, so once again this expression can be def for use, we'll have to so there are three kinds of E, remember. If this E is this kind 3, okay, which means it's like a new definition for E, so you have to increment version. If E is the real occurrence, user has typed it, yes, you don't know first time or second time, you just encountered it, we don't remember anything, right, we are only looking at local thing. Okay, so but if user has typed it, it will have its operands being versioned as well. Okay, so if user has typed it A plus A star B, because you are renaming variables also, or for simplicity you assume all variables have been renamed, so you will have A star B converted into A5 times B7, something like that. So you compare A5 with current top of at this point version stack for operand. Okay, if they are the same, that means there has not been any change. If A has 5 version here as well as in the stack of that means currently you are actually processing A5, currently you are actually processing B7. So if everything is same, then E value has to be the same, which you have seen earlier as the top of stack. A has not changed yet from last computation. If there is any mismatch, which means this first case, that between H1 and H2 there has been an assignment to A, so you have to convert H1 to H2, or you have to increase the version number. Okay, if E, so we have taken care of this E, we have taken care of this E, now these E's. This is again very similar to normal variable SSA. You have to look at predecessor block, you have to see which number you are coming from and then assign H correspondingly. Okay, so for each operand of E, you have to compare the version of operand with the top of the rename stack of the operand. So you have to look at AB, if all match, again you get the same version, if they don't match, so this is very important, if any mismatch, replace E by bot in the operand, push it on E stack. There should be a comma here. Okay, so this, if there is a mismatch, then you replace this E by a bot. What does bot say in this case? We are talking about availability of expressions. Yes? not available. Okay, so if there is a mismatch between argument what you have in your hand and argument that is there on top of stack, that means again on that path argument has changed after last computation of E, which means on that path E is not even available, not at all available. Okay, so then you say E is not available, forget partial availability, E is not at all there on that path. So you push a bot and you also push it on E stack. So on this path version of A has changed. Okay, your E has some other version, A5. So what it tells, this A and current A value you have with you are different, which means on this path there has been an assignment to A which is after the last E you have seen, which means there is no availability of expression on this path. So corresponding phi you will replace E by bot. Okay, so let's look at this example. You have the example, right? So on this path A has version 1, clearly there is no version for E, there is no E, so you have to replace it with bot. Your versioning will not match. Along this path, this is user entered expression. What did we do for user entered expression? You have to compare version of operand with top of the rename stack. So basically you have to see what A is reaching here. Okay, so since where is B1? Actually I should have had B1 here also. Just at the entry every variable has a value and B does not change at all, so B1 is here. So what will happen when you check operand stack here? At the top you will have A2 because this node is dominated by this node. This node dominates this node. So you will process it after this through child edge. So at the top of rename stack A2 will be sitting, B1 will be sitting. So there is a match of all the operands. Okay. So what you will do is the number here will be same as what you have got earlier. Okay. And what is this? The last one is A4 plus B1. How do we get a number for this? Okay, no, we have to look at this one, phi. So H2, phi of H1 coming from this path, and along this path, version number will not match because version of E will be A2. The E version will contain A2 as its argument, but the top of stack you will have A3. So these two will not match. I can do all this after the class. Okay, so version changes, so you have to put bot here. Here E will still have A2, version of A is also A2, so the two things match, so you will continue with whatever version came from top. Okay. So what are we doing exactly? Yes. A4 will get, if you are coming from this path, yes, but if you are coming from this path, this will be bot. No. So if you are coming along this path, A star B is not available anymore, right? Because whatever you computed, maybe this was 20 plus 5, 25, but now A has become 10. So you will not be able to use 25 here. It will give you 15 if you try to compute it. So you cannot reuse it. Okay. So what these phi's are trying to capture, again as I said, just like variables, they are trying to capture the two different values of expression are coming along two different paths. Now unlike variables, there are more variations. Why there are more variations? Because expression can change because its arguments are changing. So that also you have to capture. How do you capture arguments changing? Arguments will change because of assignments to them. Okay. So if you are saying I have computed A2 plus B1, but when you look at A, the version of A is A3 at current point. So clearly if I now try to evaluate A plus B, it will evaluate A3 plus B1, not A2 plus B1. So I have to keep track. Okay. So next we come to down safety. Down safety is this anticipability I talked about. At a program point P you are sitting, you look all paths towards exit. If the expression is computed along all path without reassignment to its arguments, okay, if you look down you see every path computes A star B, then you are sure that it is anticipable or down safe. So this is done because you, as I said, you don't want to introduce a new or a extra computation of E on a path where it does not already exist. This is just a mirror image of available expression. Okay. And the interesting thing is we need to compute down safety for inserted phi operators. Why? Because if a user has written it, he has written it. Why do you want to check for it? If I have written something, I don't want compiler to worry about whether it is safe or not. I am the boss. Okay, if a user has typed, so only thing if you are inserting something or as a compiler you are inserting something, then you have to worry about user's intention. If user wants to crash his program, who are you to say anything? Okay, as a compiler. When I say you means compiler. So phi computation is not down safe. If there is a path to exit from phi along which the result of phi is not used, so you have inserted a phi but then nobody is using it, or it is used only in another phi which itself is not down safe. Okay, so you are member of another phi but that phi is not useful. So it's a transitive property. And you also maintain a property called has user use. So basically if user has typed an expression, then that clearly has a real use. Okay. So down safety property, let's see, this is an inserted phi, is it down safe? So you have to check whether the result is used in some real expression. So here you can see there is a real occurrence. Okay. In fact, this is such a simple example, I can't show you down safe equal to 0. Here is H2, here it is used. Okay, so I think there is a bigger example in which you can see down safety not to be 0. Let me see if I can quickly show it to you without actually showing how it is computed. So in block 10, I have forget about everything else. It's also computing H2. Okay. So here down safety is false because H2, if you see, it is being used in H6. H6 is used in H7, but then H7 is being used. Why is it coming out to be false? Some problem. H7 is used, so H6 is being used by H7, H7 10 to 15. Okay, yes, right, sorry. So I forgot the dashed edges I have to look at, not these arrows. Okay, so dashed edges are really program edges here. So if you see there is a path from 10 to exit on which there is no use of H2. Which means if I insert my expression here, I am introducing a computation along a path which is on which the computation was not already existing. Okay. So this is an all path, every path you have to check, and if any one of them fails, you fail. Look at some other number, 12. 12. So from 12 I have to go to 17 to 14. I can keep looping and then I reach exit. But then H5 is being used here. So anytime I come here or here, no matter which path I took, I have to follow this H7. I have to execute H7, which means H5 is useful. Okay. So that is down safe. Any other one? So something which has more than one exits. 10, 11, 12, 13, 14. Yes, 14 has more, but 14 is also trivial because every occurrence of 5 will go through this use just after that. Okay. So this is much more complex example. We can do it in the second half. Now will be available, this is another property. So note that quite a few of these properties look identical, similar, but they have been broken down because some of them are backward, some of them are forward, some of them look at what is going to happen next, some of them look at what is going to has happened before. Okay, that's why they are kept in multiple separate analysis. And as you can see, this is an analysis. Overall SSA PRE is going to do both forward analysis as well as backward analysis. So it's a quite challenging analysis in that sense. What was the previous one? Downward safety is a backward analysis. Will be available is a forward analysis. Okay. These are not really bi-directional analysis. There are some analysis which go both ways. Signal analysis goes both ways. But this is an analysis which is consisting of several analyses. Some are forward, some are backward. Okay. So you have to compute two forward properties, can be available, phi's for which E is either available or anticipable or both, and then later phi's beyond which insertion can be postponed without introducing new redundancy. So the idea is, I want to find out what is the optimal placement of newly inserted computation. Okay, that itself is broken into 2 points. One is, first I find out all possible places where I can insert it, and then I only look at the last point of these where I cannot push it further down. So in a way it's a sliding kind of algorithm which inserts something, keeps sliding it down till you reach a beneficial optimal point. Okay, so together these two compute will be available. So assuming can be available is correct. So what will be available says something can be available and it cannot be pushed any more down. So now you have to insert it there. So you have to make it available there. Okay. So how do you compute can be available? Initially you can say all phi's are available. Then you find boundary phi's or the latest phi. So if a phi is not down safe, then you cannot go any further down because you are introducing a redundancy. And at least one of their argument is bought. Okay, why? That means, so it's not anticipable, it's not available. If it is anticipable, every path from this point to exit has a computation, so you are safe. On the other hand, let's say it is not down safe, but then all the arguments of E or phi have something coming in, which means on every path there is a computation. Okay. Now one of the path has bought, which is on this path E has not been computed. So now you can find a path coming from top on which E has not been computed because of this property, and you can find a path toward exit along which it is not down safe, along which it is not computed, which means you can find a path from entry to phi to exit along which there is no computation of expression. Entry to phi to exit along which there is no computation. So now if I insert my phi here or actual computation here, then it is unsafe. I am introducing a new computation on that particular path. Is this logic clear? So in some block, I have a phi where I have one of the argument as bot. Okay, what this argument says, along this second path, E is not computed. Okay, which means from entry along this path, E is not available. That's why this is bot. If there was some computation, I would have got H5 or H7. Similarly, it is not down safe, which means there exists a path from this point to exist, along which E is not computed. If I combine these two information, I have path from entry to current node to exit, along which there is no computation of E. There is no computation from here to here. There is no computation from here to here. Okay, so on this whole path, there is no computation of E. So now if I insert E here, if I insert, let's say this double E here, I am introducing extra computation, unnecessary computation. Because at runtime, maybe I am unlucky, I am always going through this path. So I am unnecessarily executing E again and again. Worst case, E might create an exception, E might fire a rocket which might hit some country, which is not good, okay, some friendly country. So this is boundary phi, this phi we should be careful about. So we have to mark all boundary phis as false. These are not safe, these cannot be available. Now this false value has to be propagated through chain of def and use to other phis, excluding edges along which has real use is true. Okay, what does that mean? If you have discovered that some user has put an expression, then that user has put, so you have to ignore those paths, but every other path you have to propagate your can be available thing. Okay. So I am giving you intuitions, actual data flow values are also there in the paper. Later will determine latest final or a final insertion point. So again, you initialize later to true wherever can be available is true, otherwise false. See, if can be available is false, there is no point in checking later. Okay, because you are not going to push that down. Assign false for phis with at least one operand with has real use flag to be true. So if a phi has one of the arguments already set to true as real use, that means it is getting a real use. Okay, you don't need to push it further down. And this false values now you have to propagate to other phis, because false tells you have already found a value, you don't need to push any further. Okay, so laters will be true for those phis which are possibly available, basically can be available, at the same time they do not have any real occurrences. So now you have to create your own occurrence. So these are safe points for which along certain paths no real use is arriving. So you have to introduce it. Okay, and this gives you insertion points. So you do for phi operands along the corresponding predecessor edge. Okay, so why we are doing this? Because phi really don't have any meaning. I could have done it in the argument of phi itself, but at runtime then I have to move it to predecessor. So directly I am doing it at predecessor. Okay, so if ith argument has this insert flag to be true, then you will insert it. When will insert be true? First, will be available has to be true. Basically we have decided, yes, I have to make this available, and the corresponding argument is bought, which means along that path actual expression is not available. So remember what we did with partial redundancy. So A star B was computed here, A star B was used here, and on this path A star B was not there. So what we did was we introduced a temporary with A star B computation here. Okay, so where do we do it? Slightly above, just before the thing. So all this is doing exactly the same thing. On this path, you can push it without any issue, and it is actually not available. So then you insert it. Okay, so again, all these are just equations. Has real use is false. R guy is defined as phi prime with will be available, phi prime is equal to false, and all this. Okay, this gives you the insertion points. After that, you just have to do some finalization. You transform the program with redundancy class variables into a valid SSA form. See, those redundancy class variables were temporary things we introduced to keep track of expressions. Now you remove them and actually introduce corresponding expressions with the variables in SSA form. Okay. At this point, you have to decide for every real occurrence of E whether it is a def or use. Why this is important? If it is def, you have to say T0 equal to A star B. If it is a use, you have to say replace that by T0. Okay. So for every phi with will be available being true, insert E. Okay. So again, these are a lot of equations. I just yeah. Okay. So I think all this we will do in an example, this example after we come back from, we are already late. Okay. So we'll stop here. Last things I want to do on the example. So rest of the evening today we will work on the big example that we have seen. I think we are almost done. Okay. So I think we are 10 minutes late, so we will start at 2:10. Okay, after lunch.